Hey everyone, thanks for joining us for our first webinar of 2021. We're super excited to be joined by Bruce Tate, who is always one of our most popular webinar hosts and always has a bunch of really exciting knowledge to share with you guys. It is a really exciting time to be talking about Elixir. The first couple of months have seen some really exciting news, and you can really feel the energy from not just inside the community, but people from outside of it as well. So it's a really cool time to be talking about Elixir. And today specifically, we're talking about software lessons from hardware projects. This is a webinar that is based on one of Bruce's and Groxio's courses. You can find out more about them at Groxio, Grox.io, and you can either buy the individual courses, this one is the Nerves one, or you can sign up to a subscription. On top of that, we're also hosting CodeBeam v America next week, which is our first virtual conference designed specifically for our community based in the Americas. Bruce will be joining Jose Valim for a fireside chat there. There's over 40 talks with a bunch of specific standard talks, as well as interactive fireside chats, question and answers. So we really are trying to bring as much interaction and energy into the virtual conference environment as possible. And it would be great to see as many of you there as possible. So when I send out the emails of the recordings of this webinar tomorrow, there'll be information about Groxio and the courses that are offered there. And there'll also be information about CodeBeam v America and all of the fantastic stuff that's available at that. And with that, I'll hand over to you, Bruce.
Hey, thank you so much for that kind introduction. It's been so great throughout this difficult 2020 season to have Erlang solutions as not just in the professional relationships, but the personal ones as well. So thanks for that, and for the folks there. I would like to echo what Anthony said, that that I do this basically as a part of the Groxio project, which is essentially my attempt to write professionally in a time and space when writing professionally is kind of on the decline. So if you want to follow us along at Groxio, essentially we're on about a 3-month cadence for individual projects, and you can buy a la carte the ones that have already happened, things like OTP, Elixir, and Nerves. You can also buy, we've also done Live View, which is our most popular module. You can also buy a la carte. So you can buy those a la carte. You could also buy those with an annual subscription where you get everything on the site, and you don't get a hard and fast schedule. You essentially get to read about the things that I like to talk about. And if you're more traditional, then there are a couple of books that you have an opportunity to read. We're going to talk a little bit about designing Elixir systems with OTP. And if you've been following this series, we have a couple of lessons in there that I'll refer to pretty strongly, but that's where to find them. But also on the left-hand side, there's a book I'm excited about. I'm writing with Sophie De Benedetto, and if you've ever spent any time on Elixir School, you have likely found a lot of her content. She's just extremely prolific and a very gifted author, and I'm excited to work with her on a project. And we're going to talk about a number of the concepts in that book. And as you can imagine, just like hardware is not all about the hardware, the ones and zeros that flow back and forth to the individual pieces of the device, most of live view programming is getting the architecture right. So you're going to see a number of the lessons from that book as we go through this presentation today. So I've got a couple of warnings coming into this. First, this is a software talk about hardware projects. So if you are in this to find the latest what's happening with Nerves, then you're probably going to be a little bit disappointed. What we're going to talk about instead are the software lessons that that I learned when I was going through this. And I'd also like to point out that we're going to be moving around. So we're going to spend a little bit of time in the presentation, and then I'm going to walk you through some of the code and point out some of the code lessons as at a high level, and then we'll drill down into the individual projects. So what I'll try to do is spend some time at a high level introducing the concepts, and then I'd like to drill down into the individual projects to kind of show you some of the things that I worked on along the way. And as a result, it might seem a little bit disjointed in terms of working on the desktop, but I hope that that I'll make up for that disjointed experience by showing you what was actually happening as I was making the decisions. And I have a couple of people to thank. Primarily, I'd like to thank the OTP team for building such a beautiful abstraction, and also the Nerves team. But I want to call out Frank Hunleth. Frank has been instrumental in helping me design and work through this particular piece of the project. I mean, just absolutely instrumental. Fantastic man, fantastic programmer too. But he was able to kind of look my stuff over, make sure it was idiomatic for Nerves, make sure that there weren't any major holes, and keep me from getting stuck. And as a result of that collaboration, we're actually going to be building a line of books that basically take one particular software lesson out of an individual Nerves project. And the first one up, you're going to be building the binary clock that you see behind me, where these ones and zeros are implemented by individual LEDs. So with that long preamble aside, let's go ahead and get started. And we're going to start with some of the lessons in designing Elixir systems with OTP. And if you've heard me talk at all in the last couple of years, I've really been trying to promote ideas that are that come with these mental mnemonics and essentially ideas that make learning Elixir more accessible, both on the broader sense as if when you're dealing with things like OTP and holistic systems, and also in the smaller sense, what are the things that we can do from an on-ramp perspective? So this was the beginning of that thought process, and gosh, I think it goes back, the book goes back, what, about 2 to 3 years, where I was working with James Gray, and the concepts in this book are really his mastermind. And what I did was gave a voice to the layers and the structure of the book, and kind of allowed James's ideas. I helped get the writing process out of the way so that James's ideas could come through, and I hope it shows. But this design philosophy is based on the sentence, do fun things with big, loud worker bees. D for data, F for functions, T for tests, B in big for boundary, L for lifecycle or supervision, and worker bees, which are workers, which are effectively dependencies in this particular world. And so what I wanted to do when I started this Nerves project on Groxio is effectively think through what this layering system would look like if we applied the same ideas in our hardware designs as we do in our software projects. And so the collaboration has been a lot of fun, and having an inside look into why things are done the Nerves way helped me actually blow out this architecture. And it turns out when you're in a hardware project, this thing looks very much the same. Let me see if I can, I don't know if you guys can see this box, but I'm going to shift it out of the way just in case. But effectively, the big black box is the OTP thing that we're talking about, but this whole layering structure looks very much the same, when you're dealing with a hardware project. And in fact, the difference really isn't a difference. The nuance is that an adapter layer is really just another layer that sits in the boundary. And typically, my goal as I work through any project was to build something that could be one thing that could be run three ways: on hardware, in development, and in test. So eventually the project that we wound up building in that Groxio layer was this clock. And yeah, it's kind of a geeky, nerdy user interface. You can think of it as the clock with the worst user interface that's ever been created, where you represent the seconds with the bits that make up a second input, right? And so if you think that if we need, if we have 60 states, then I could take 6 bits, which can actually represent 64 states, to do the seconds, another 6 bits to do the minutes, another 4 bits to do the hours from 1 to 12, because I can represent 16 states with those 4 bits. And then another one in the United States, we have this AM PM indicator. And so that's kind of the project that I built first. And then as if I wasn't enough of a glutton for punishment, we added in this idea of a sensor hub. And the thing that you see in that image is a ambient light sensor, which is pretty cool. So it has this beautiful user interface. Well, first it has a beautiful hardware interface called a quick connect cable, which meant that I could set this whole thing up without doing any soldering. Well, I say I didn't have to do any soldering. Frank actually sent me this pre-soldered board with the quick connect header. And that's, if you see the Raspberry Pi underneath and you see that tiny red board and the tiny 6 soldered connections, that's the quick connect header. And then that thing uses an interface called I2C that effectively puts all these things on the same accessible bus, where I can read a value, or I can write a value, and then based on the thing that I write, that's really a command that gets put on a register, and then I can read values off. In this case, it's ambient light, but we also had sensors for the project that did things like temperature and so on and so forth. So it's really a pretty cool project. But I want to talk first about this first project, the binary clock. The thing that you see sitting behind me. I don't know if you still have access to my face, but this is the binary clock. You see we're blinking through seconds here, with the least significant byte all the way over here and the most significant byte in the PM indicator all the way here on the left. And gosh, the woodwork was almost as fun as building the rest of it. But so one of the things that Frank really taught me, now I tried a NERVS project a couple of years ago. I have a mentoring program that was formerly Elixir Chat, which chat stands for Chattanooga, and also kind of the chat server that everybody built first with Elixir and Phoenix channels when they came out. But also Elixir Chat, because we talk about Elixir there, and the idea is to ramp up, is to help underrepresented in technology have a little bit more of a voice. And we built a photo booth, and that project was very difficult. And I think that the reason that it was difficult for us was that we tried to do too much at once. And with this particular project, the thing that I started with is the thing that everybody starts with. First, you decide, you make sure that you can use the tools on your desktop to actually upload some firmware or the project that's going to make that Raspberry Pi go. And so we did that initially by sliding the card into the computer, then running a mix firmware and mix firmware burn, which are the commands that copy the program onto that little disk, and then you plug it into the Pi. And that's one step, right? And so this is important to have one logical step at a time that can give us small successes. What it felt like to me was working with hardware the same way that I worked with test first development, right? So I write a little test, make the test pass. And so I was turning red lights green all day. So this approach really resonated with me. And Frank basically was able to walk me through the small steps that would make up the project. And the next step was to do this thing called Blinky, and it's the application everybody writes. And what you see in front of you is a circuit, and the kind of the dashed triangle on the left-hand side, that's a ground, and you can look at that as the, that is a power source, and you can look at that as the positive end of a battery, right? And then there's the squiggly line that you see, that's a resistor. And what that does is provides a little bit of load to the circuit so that it protects the components. And basically the laws of math around this, Ohm's law basically means that you have to have enough of a load on the circuit so that the individual pieces are protected and it performs the way that you expect it to. And then the next thing is an LED, which is just one of these blinking lights here. And the other end, you can look at it like the minus terminal on a battery, that's the ground, right? So things flow in a circle from the power source, which is called GPIO, or general purpose input output. It's essentially one of the pins on a Raspberry Pi, and through the resistor, through the LED, and then out through that piece. And so the nice thing about it is this is an easy circuit to build, especially using a temporary medium called breadboard. And so after you built this, then you can go, that's one tiny step, and you can verify that. And then you could turn around and you could turn that on and off with a with that initial project that where we were just burning firmware, right? So we took a download called the Nerves Quick Start, and we installed it on the Raspberry Pi with this Quick Start Circuits Quick Start program, and then I could shell into my Raspberry Pi using just a USB cable to micro USB. I could run IEX and I could blink that LED, and oh, is that satisfying? It doesn't sound like it should be very satisfying, but when you can control that the real world with your Elixir program, it's kind of something moves in Makers when that happens. So effectively, this is what the same circuit looks like on breadboard, and you can look at breadboard as a medium that connects things, right? So you could see that this input kind of flows. There's the gray lines between the components, and there's green wires, not necessarily green, but there are connections that run across all of the horizontal lines of that breadboard. So I could just plug the components in. I can send a wire out to one of the pins on my Raspberry Pi, and then another pin on the Raspberry Pi for the power and the ground, and I am off to the races, and I can light that LED and control it from the hardware. That's another small step, right? So now I have a working circuit, and I can kind of, so it's confidence building to turn these red lights green, or in this case, literally light a red light or a green light. So eventually, when we're thinking about these layers, the do fun things layers, this is a lot to take in, and it's a lot to work with, and it's definitely not one iterative small step. So essentially, I don't think about all those steps at once. I essentially build this boundary layer, right? And remember, that looks like sort of like the adapter, and so I build this adapter that knows how to open the GPIO pin, turn it on, that lights up the LED, and then turn it off with functions that are, on and off, right? LED on, LED off, or whatever, and open. And then I have a working a tiny little bit of a working connection. And this kind of process, this code, fits in the boundary layer because when you are working with hardware, the operations are uncertain. And the boundary layer is where uncertain things live in our architecture, right? So sometimes if you've seen my talks before, you know that that I kind of light up and sit a little bit taller when we talk about this place called Pipeland, right? So that's where everybody learned Elixir, where you take the take outputs of one function and feed it into another function, and then you get the value of another of both those things connected together. And these types of transformations represent the way that programmers think. And the boundary is a place that is also effective in Elixir, but the composition is a little bit different. So when you're composing over failure, you have to manage exceptions, or you have to work with these error tuples. And so the composition with pipes gets more complex. So we compose things with a structure called width, or a programming construct called width. Okay, so so that was a small step. It let me start to build a little bit of software where pretty much all of it lived in the boundary layer. One layer that talked to the hardware, and I was done. Small step, small step. And then I said, well, what if I took these GPIO pins and I connected them into another bunch of circuits? And you could see the modular nature of this, right? It's really the same section over and over. It's connected on my breadboard, and I, rather than tie everything to its own ground, I just tied all those to one rail on the pin that's connected to the ground, and then connected the other end of the pins to different GPIO pins. And at this point, I could control multiple GPIOs by basically using the same setup that I had in the previous program. And that was cool, right? So at this point, I started thinking about the concept of a clock. And I said, okay, Frank, let's go. Which ones of these GPIO pins are can I actually use? Because some of them are overloaded and some of them seem to have various brightnesses and at various levels. And my clock is not looking like I expected to. And Frank looks at this thing and he says, and I said, I don't like that, And he said, well, and I didn't like the sound of that well either, right? Because that meant that I was going to have to do something that was a little bit more complicated. And of course, Frank talks me down. He says, hey, small steps, right? Well, what you need is effectively something that can control the brightnesses on something called a peripheral interface, a serial peripheral interface called a SPI, right? And so he said, you don't want to actually deal with all of these as individual LEDs because you'll be disappointed. Well, first, the Raspberry Pi might not even have enough power to drive them all at once, right? And second, if it does drive them all at once, some of these, as you've noticed, are kind of overloaded in purpose. And so you might not get the same brightness and the consistent look that you're looking for. And third, if you are ever going to mention me in conjunction with this project, you can't produce hardware that looks like that. That's not the right way, right? The right way is to use something that looks like this, right? That's a SPI interface. And so what it does is it uses the inputs on the left-hand side, and you can see that those are labeled. That bottom one is a voltage, right? That's where it gets power from the Raspberry Pi or from some type of power, external power supply, right? And then there's a ground. And then there are individual inputs from the SPI interface, right? And so there are libraries that work with this. And so I looked at that thing and I said, where are the pins that I could hook things up to? And he said, well, don't you see the header boards or the headers below? You're going to have to get a soldering iron, right? So I got a soldering iron and I kind of wired all this stuff up. And then I was able to connect LEDs to all those numbers. You can see that they go from 1 or from 0 on the lower and the lower left, all the way in a horseshoe shape, all the way up to 11 on the lower right, up to 12 on the upper right, and then to 23 in the upper left, right? So it's in a horseshoe shape. And it turns out that I can send a block of brightnesses to this thing all at once, right? And then I started planning out my clock. And so this was actually a baby step because I already knew how to build circuits. I already knew how to connect LEDs. And this worked great for me. So I set this up, and then rather than connecting individual LEDs, I took these strips called ribbon cable and I hooked them up and kind of took every fourth pin. And if you'll look at it, that's the way that this is structured. So you can imagine one connection that goes all the way across there and you skip every fourth one. And I was able to solder things up that way. Everything worked great. And I was able to build the hardware side of my clock, right? You could even see those ribbon cables connected up. Okay, so then I started thinking about my software structure. And I said, you know, I am ready to take the next step. I don't think that it's a smart thing to do all this work in the boundary, right? What I'd like to do is expand on this to work with different layers in the system, right? And so it turns out to solve this project, to build this clock, I needed almost all the layers in the system. That is okay, because I could build those one step at a time. I had the data and functions, and then the test for those data and functions, and that could be my functional core. And the functional core's job would be to take a time and then extract the individual pieces of the time and compose and break those down into ones and zeros, and then take those ones and zeros and shove individual brightnesses through that interface, through a software interface in the circuits package called SPI, right? So then I knew that I would need the software side of that. So let's take a look at what that looks like. So let's see if I could find this. This is the binary clock. So let's bring this down here. Okay. So one of the things that I've been working on in Elixir is ways to actually teach concepts to new Elixir developers, right? And so one of the concepts that I think about is CRC, right? Another way to think about this is inputs that pipe through, right? And then I can pipe into a constructor, and then I could pipe that constructor into a reducer. And then I might have several of these reducer steps, right? So for example, maybe the constructor is opening my GPIO pin. And then maybe the constructor's job is to feed that to turn LEDs on and off. So maybe I say, hey, I have a reducer called on, and then a reducer called off, and then a reducer called on, and I could blink an LED that way. But anyway, the other end of this CRC framework is a converter. And if you think about it, if you're thinking about an OTP program, building things this way in a functional core where you can live in the beautifully predictable place where you can pipe things because the data has already been validated, because there's no unpredictable things like database access or anything like that going on in this space, right? These are all kind of beautiful things that are happening. And then there's this constructor. So I could live in this world, and then I can think about the OTP. Well, what are the callbacks for OTP? Well, this callback is the init, right? And constructor, or I'm sorry, this callback is the constructor, and it takes the inputs, right? And then these callbacks, the reducers, are all going to be in the handle call and handle cast, right? Well, sometimes you have a handle call to return something to the client, and then you have to take the state that's created by the constructor and you have to feed it into a converter, right? So I'm not saying that all Elixir programs take this shape, but I am saying that in OTP, if you can think about your cores, about code that you could extract and feed into a core, and you can build the code in this shape, even if you don't have all the individual pieces of this, right? You are going to be better off because they're going to map well onto your OTP program. So in this case, what I really need is inputs. In this case, the inputs are the time, right? And then I need to feed that time into a constructor. And then I need to feed that into a converter called to LEDs, right? So this constructor, the job is to build a data structure that is representative, that is easy for intermediate computation. And this job is to take the intermediate computation and prepare it for consumption for the outside world, right? So in this case, I build the AM/PM indicator with a simple division, integer division. I build the hours with effectively modulo division. Then I have the minutes and seconds. I just extract those directly from the inbound time, and I'm off to the races, right? And then when it's time to actually feed that into the boundary layer, well, what the boundary layer is going to do is all of this work, right? So hardware is putting the right bits and bytes in the right place. And so in this case, I need to think about how I build my LEDs, right? In this case, I take each of the numbers and then I feed them into a function that says, give me the bits, which are ones and zeros, but they're zero padded so that they're all the same shape, so that I have chunks of 6 that I can work with. And then the top of the clock, remember, there's that horseshoe shape on that board. So everything on the top of the list, I have to reverse because that's going to be in the reverse format. And at the bottom, these are not going to be reversed, right? So, but I can build this in the beautiful world called Pipeland, right? So I take this, then I flatten it, and then I send it through my formatter that it's going to be able to format for whatever platform I'm on, right? And maybe that's going to be formatted for a host. Or maybe it's going to be formatted for a hardware target, but that formatter is going to allow me to run the same program in 3 different ways. Okay? And so all of this is all straight math, right? There's there's binary bit strings. There's on the if I'm running if I want a pretty format which works well in IEX, I'm going to convert the zeros into dashes and the ones into stars and so on and so forth. But the idea is that all of this can be written very concisely because it's very certain. Okay, so let's move on to the next part of the project, which was to build the server, right? And so this server, you're going to be amazed at how thin the server for this clock that's sitting behind me, right? Well, what does it look like? The API just knows how to start. It has a function called tick, and you might be surprised that there's a function to send a tick message. Well, don't you usually send ticks periodically with an automated per second mechanism? Well, yes, you do on the host and on the hardware. But remember, we wanted to run the same program 3 different ways. So some of the time we want to send the ticks in a different, we want the test case to be able to advance through the individual times on its own. And so that's why we have a tick piece of the API. But otherwise, I have an init API, right? And what is the init tied to? Well, it ties to, its job is to open the SPI bus. I love that SPI bus. I feel kind of like important and cool, right? And then I can send on an even interval the tick message, right? And then I build the state for this thing, which is effectively, it takes a time zone and a SPI. And then all I have to do is handle do handle info, right? And what does that handle info do? Well, it processes the tick message. It says I'm processing a tick, and this is just to be instructive. So while I'm running on the host, I get some feedback as I go, and then I light the LEDs. Well, what does that look like? Well, I basically transfer the bits. I transfer the bits to the SPI that I create with my core. What does that look like? Take the time zone, build a new time with it, feed that into my core, convert that to LEDs. And I take that specific format, that time that won't fail. If things break, they're going to break here. I get an exception, let it crash, and I'm off to the races, right? So in this case, my server is really, really skinny, and the only hardware interaction is right here, right? And this is actually, this has a stub, so this will work the same. Well, it actually won't do work if you're on a target without a SPI interface, but it'll work the same otherwise. So this was a beautiful abstraction for me. And then, so if we look at the Designing Elixir Systems, this is the boundary layer. So we had the core, which was data, functions, tests. If I look at my test, it's really skinny. Actually, my tests aren't implemented in this particular project. I'll post another one that has test code a little bit later on. This particular project was for a walkthrough, but then there's the application. And what does the start look like? Well, I start my binary clock server in the Eastern time zone, and that's it, right? And that is it. It is beautiful, beautifully concise, beautifully simple, and I'm off to the races. Okay, so let's pick up from here. So I want to reiterate that Frank and I both agree that when you design your hardware projects in this way, there are 2 places that you want to consolidate your code, right? Of course, we've already talked about this idea called pipeland. And pipeland is this magical place where things are predictable, where you have individual, where you have certainty, and that means that you can use pipes to work with direct transformations without the risk of things failing. right? But there's this other place that's pretty magical in its own right, and it's called Hostland. So this is being able to work with projects on your server, whether they're on your host, whether you are working with something that with a project that has specific hardware requirements or not. Whether you're working on the boundary or the core, it matters a lot. It improves your cycle time if you can test and you can run a lot of the project, as much of the project as possible in the host land. If I look at this overall project, this thing all works, minus that small SPI hardware layer, based on it with the code that we've already built. And ironically, the adapter layer here, I didn't have to lift a finger to actually get to run, because all the work was done by the circuits team. So I didn't have to worry about making this run on the configuration, on the host configuration. So it really made this project easier to work on. Okay, so effectively what we're doing, I want to just kind of reiterate this, we're running the same thing 3 ways. We take that core layer, we can run tests based on that. We take that server layer, and then we have the lifecycle management. So this is your do fun things in the core with big on the server, and lifecycle. That's your loud. You're loud. So and then the only thing that was different about this and a typical software project is the adapter layer, right? Because the adapter knows how to run on a host versus a test versus a target. And I want to show you what an adapter looks like, but I don't want to show you what it looks like in the context of this complex application. I want to show you what it looks like in the case of a blinking LED. So I'm going to grab this second code editor and put it in a place that we can kind of see what's happening. But the magic piece here is actually something called a behavior. And think of a behavior as a program that somebody else wrote that calls your code. Now, most of the code that we write is essentially, it's an old programming paradigm called a procedural paradigm, where you write code and then call functions that somebody else writes, and your program stays in control. Well, a behavior flips that on its head, and the idea is that the behavior actually controls the implementation and calls back into individual implementations for specific parts of the problem, right? So in this case, I have an LED adapter, and I could do 4 things with it. I can open it, which opens up that GPI open, gets it ready to use, right? Because this is going to turn into an Erlang reference, also a reference in Elixir. Then I can use that reference to access that GPIO pin, send voltage to it with an on, take voltage away with it off, or flip it with a toggle, right? So it turns out that this open implementation doesn't really matter whether you are in which implementation that you're working with, right? So actually, this does matter, right? But on this, in this case, all these implementations, I'm going to call whatever the adapter implementation is. I'm going to call the on function, pass the LED. I'm going to call the adapter, pass the off function, pass the LED, and so on and so forth. I want to point out a bad pattern that I have here. In this case, I'm using the CRC pattern, but I'm composing over tuples, right? And the bad thing about composing over tuples in this way is that I have not marked the individual components. So it's better to compose over a struct with named elements, or at the very least a map, right? So this should be a map implementation instead. Okay, but then this couldn't be simpler. I get my LED, which most of the time is a reference. Maybe on the test layer, it's an integer or something like that. Then I get an adapter, and the adapter is just one of these modules, test, embed, or dev, embed, or test, right? So the development implementation of on is just, hey, I'm on, log it, right? And then I set an attribute on my struct to true, right? And all it has is like a pen with a default to 0. So maybe I say open 4 to remember which one 4 was as I'm working in IEX. And then when I'm confident that this behavior is working, then I'm going to plug in a test implementation, and I'm going to write a set of tests for it. And then once that's done, I'm going to move on to my embedded implementation. And only then, after I'm confident that the layers are working correctly, do I start to work on the individual hardware implementations. In this case, it's just GPIO, open the pin to open it up, write to it, write a 1 to turn to send current to that pin, return the LED so that it composes, and write to it, right? So you can see the CRC working here, right? This is the constructor, and I could pipe that whatever comes out of here into a reducer. So you can imagine creating a flow that says constructor or open, pipe to on, pipe to sleep, pipe to off, pipe to sleep, pipe to on, and so on and so forth to blink something 3 or 4 times. And everything's fine, right? And so the test implementation is pretty straightforward. What this does, though, is it tries to track it's not just the implementation, but the history of the calls that's important, right? So my reducer remains the same, but I'm going to change lit to true, and then I'm going to change the history to record what has happened on this, right? So I'm going to add on to the stack for on, or off to the stack for off. And then the toggle just calls the implementation underneath, and so I still get benefit of tracking the history. Okay, so now let's move on to the next piece here. Okay, so at this point, I'm ready to send the data to the SPI interface, which it's going to remember the inputs are going to flow in. So it's going to use the circuits.spy library. It's going to transfer a bunch of bits using like a waveform, right? This is a serial transport of multiple numbers. And so the way that this kind of device works is that I can send 12-bit brightnesses to this board, and I can send up to 24 of them. And if I want to send more, I just daisy chained these particular chips. All the 6 pins on the right-hand side, those are outputs, so I could just chain more together, and I could use Circuit SPI to connect things together. And so this is what the data looks like, right? Remember, we had the 0 pin on the left-hand side, 11 on the right, and so it counts up, and those are the ones that I have in reverse. And then on the top, it starts at 12 and counts down to 23. So that's why we had that reverse. And then I connect meaning to those pins by dropping in these pieces, right? So the seconds are on the lower left, and the minutes are upper right. Hours, lower right, in AM, PM on the upper right. And obviously, we're not using all the bits. We only need 17 of them. Okay, so now I want to shift attention a little bit to this idea of a sensor hub. And I use the word hub pretty loosely here. All we're doing is collecting data from sensors, and we're collecting it with a straight Raspberry Pi that's connected. The Raspberry Pi is on the left. It has on the standard Raspberry Pi pins. The first 6 of them can be used with a standard called I2C. So essentially, we can connect them with these short cables, and then effectively we can look at the sensors like the ones on the lower right. With the lower right one, you can see that's a VEML 6030, and that means it's an ambient light sensor. And you can see that in the very middle of the chip, there are these two, well, there's this tiny square and 2 larger rectangles. Well, the tiny square, that's the actual chip, and the rest of it is just a board to make this convenient for makers, right? So this is what it looks like connected. And this project was a little bit different for me because it dealt with dependencies in a way that I haven't worked with before. Works with dependencies using this concept called a poncho, right? So you might have heard of umbrella applications. Poncho application does very much the same thing, but with a little bit less benefit, a little bit less ceremony. So think of a poncho as just a directory. So this is not an Elixir project at all. So, and then the directory might have several projects in it, and maybe 2 of the things in the directory, maybe they have nothing to do with Nerve's firmware at all, right? And by firmware, I mean, does this project build the bits and bytes that need to be installed in a bit of firmware? So you could actually have things in the list. So there's a firmware project, and the firmware project's job is to do lifecycle, a little bit of configuration, and glue code, so to make things like the different sensors that might have in different projects that might have different formats, but we make them more common, right? So maybe there's another project's job, it's to talk to hardware, but we don't need it to be a firmware project in its own right. So maybe this is a wrapper around one of the sensors. So maybe its job is not to build a NERVS executable, but to use features like the I2C library that we talked about earlier, that's part of circuits, again written by Frank Unleth, which allows it to talk to hardware over a standardized circuit. But the idea is that if it's not if you don't have to have it be a firmware project, then you don't make it a firmware project. And then maybe there's a third type of project, that's sub-project that's in the poncho that is just pure Elixir stuff. So if I look at this thing, each of the 3 software projects, or each of the 3 element sub-projects in a poncho, have different characteristics. The one on top, its job is to manage lifecycle, right? And remember, that's the supervisor. If you're building a straight Elixir project, this would be mix new -- sub. But since this is going to be the firmware project, this is mix nerves.new, which also gives you the supervisor. And so it's going to have things like configuration and glue code. So if you're building for a specific target, every specific target will have its own poncho project, right? And what that does, it keeps the configuration simple, and glue code allows me to stitch things together to make things that might be rough a little bit more uniform. For example, I have in the Sensor Hub project, different sensors have different interfaces, so I can standardize them with a little bit of glue code, right? And so the hardware pieces are very often gen servers without the lifecycle management. So for example, the gen server for a sensor might be implemented in a library called SGP30. I think that is our that's our sensor that handles. It's one of our sensors. I can't remember exactly which one it is right now, but you can check the NERVS project. You can check the links that we'll provide after the fact. We'll send out the GitHub projects that these are related to, and they're all on Groxio Learning, the GitHub. And then you would also have adapters, and remember, adapters are slices of code that let the same project run in 3 different ways: once on test, once on the host, and once on hardware. And then the rest is pure Elixir. So a good example might be the pub sub that we used as the hub part of the sensor hub. So in my project, I had the pub sub and broadcast extensions. Okay, so for the rest of this project, I'm going to take about 10 minutes to walk you through some code, and then I'm going to take some questions. Okay, so let's look first at this at the Poncho project, right? So if I do a directory here, this is simple, right? It's a Poncho. There's nothing in there but the individual mix projects, right? So there's the broadcaster. That's my pure Elixir project. That's the thing that effectively does publish and subscribe. It doesn't really care about individual hardware, right? All it needs is a tiny little adapter layer, which is provided in the glue code of the sensor hub, to actually make the outputs of individual sensors the same. Okay, so let's look at these one piece at a time. So first, let's look at probably start at the top. So let's look at the sensor hub. Okay, so in this sensor hub, this is the glue code that we were talking about, right? So all this is it is a module, or it is a struct that knows how to talk to a sensor. These are the fields, this is the name of the sensor, and then there are functions that know how to read the value of a sensor, and a function that knows how to convert the value of a sensor, right? And so for the individual sensors, I have individual implementations for them here, right? And the reason that this is important is that I don't control SGP30. That's a library somebody else wrote and that I used for this project. I also don't control like the BMP sensor that has. I think that SGP is like an air quality sensor, and BMP sensor has things like it has like some weather values, and I think it might also have some air quality, but it also does barometric pressure. So it's a pretty decent weather quality sensor. And there's another sensor called the 680 that actually works with this API also. So either one will work with this particular implementation. But anyway, so you can see that these are very skinny wrappers around the API things for these things, right? So get the state, read the sensor, take a measurement, right? Those are, and then the convert. So all the convert does is grab one measurement and collect it in a way that's convenient to understand. And which fields are connected for each measurement? Well, those are the fields right there. Okay. So we said that a firmware project has 3 jobs. One is configuration, and of course, a lot of the configuration for such a project is done in Mix. And in NERVS, there are three different kinds of dependencies: those that run on the host, and and other targets. So so it says dependencies for all targets. This means all targets, including hosts, right? And this is all targets, which means this is a target, meaning it's not a host, right? So so these dependencies get packaged for your Raspberry Pis and Grisps and things of that nature, but not for the host that it's running on, right? And in this case, these dependencies will work fine. These will run fine in the umbrella project, but the purpose of this thing is actually to wrap up everything that we're building for a firmware project, right? And then the last job is lifecycle. So where do you find lifecycle? Where do you find the lifecycle? Well, you find it in application.ex, right? So in this case, we have to do a little bit of work in the start link to set things up for PubSub. And so in our particular implementation, this was just going to be running in my home. So I thought I'd do the lightest weight thing I could think of. So that's just PubSub over process groups. Obviously, if you don't have control, if you can't secure the target, you can't secure the network, then you ought to be using something else. But for this particular project, process groups and Erlang distribution work great. And so in this case, all the dependencies, in this case, I started as child dependencies. So there's air quality sensor, there's weather sensor, ambient light sensor, and then the everything that my PubSub needed to start. And since this required PubSub, I also had to start the PubSub supervisor, right? And so this is it's the name of that supervisor is the sensor hub for PubSub. And so the broadcaster, these are the elements that I'm starting here. So probably should move some of this stuff into configuration. I just had not gotten around to that yet. Okay, so that's the sensor hub piece of this. Now let's take a look at what's next. So we had the sensor hub. Now let's look at the wrapper for an individual sensor. So I worked with Frank on this one. It took me a while to get right, but the code, the result is pretty pleasing. In this case, the reason for being for this particular application was to present an interface that was effectively a server interface. So many times you sometimes see me surface a boundary and a core API in separate places. In this case, I thought, well, the reason for being for this thing is to provide the server implementation. So I'm just going to implement the boundary at the top level, right? And there are just two major APIs, right? So there's an init, and there are init versions that work where there are init versions where you've passed a specific address and I2C name. If you don't pass one, we'll try to guess one for you, and then call the init with those values plugged in. And so think about this in CRC as the server function that goes with the constructor, right? So if I were in a core, I would use the core features. And in fact, I do use a core feature. This is a configuration. Well, what does that look like? Well, these are the individual bits and bytes that I'm going to pass out to my individual sensors. And once again, on this particular layer, I don't need a reducer. I'm using CRC, but I don't need a reducer. I just need a new one, a new structure based on the inputs. So I have one that can just use this defaults. If you need to override those things, you can, but the toInteger effectively just does it builds the register that we're going to send to the individual device. Right? So that's a whole job of this thing, and these are just individual bits and bytes that I have to. So here, these are the individual bits and bytes that I have to control. It's a light sensor, so it has two things that you'd expect. The aperture and the shutter speed, right? We're gaining time, and so I feed those. I take that configuration, and then I basically write that to my I2C address. So I'm writing to, this is the bus and this is the address of the bus, and I'm just sending this configuration. And then I'm going to pull the sensors every second, right? And so my state for the whole thing is I need an I2C, I need to remember the address, I need that configuration for converting, for reading the values later. And then I want to record the last reading so that when people ping, when people want measurements, I'll be able to send them, right? And so there are two different APIs, one to tick a timer, and the other one to send a measurement. And those call these two very skinny functions here. But then there's a communication layer that knows how to talk to the hardware. This is for the I2C discovery that Frank's graciously added to I2C for the benefit of this project. This knows how to open it. This writes the configuration, and this reads the value of the light sensor. And that's it for that piece of it. And we can take a quick peek also at the broadcaster. And this is just straight Phoenix PubSub. So if I look at the requirements, I'm not doing a whole lot here. That is, in fact, you could see that I don't even add any dependency except Phoenix PubSub, right? And this is a very skinny layer that sits on top of Erlang PG distribution. Okay, so if I look at the broadcast here, I essentially set up my sensors, right? These are passed in. And so this can run, so I can basically play with this thing on the host. Remember, we want things to run 3 times or 3 different ways. Well, one of the ways is on the host. Well, my test sensor, I thought, let's just read the time. And so this basically builds a little wrapper of the same form that you saw in the sensor hub, that glue code. We have a name and the fields, and then what do? I read it, and then the time is just UTC now, right? And then the convert, I don't do anything to convert it. And so then I could see the times tick by as I run this, when I run this thing. And then so what does this do? With every tick, I do a state, I'll pipe that to measure, and I'll pipe that to publish, right? So this function takes a measurement, right? So I just walk through all the sensors. I'm going to pipe it into, this is just a for comprehension that's going to be fed into an empty map, and I'll collect the name of the sensor and the converted reading, right? Sensor read, sensor convert. And then I publish the reading with the publish, subscribe, broadcast. And then all that remains is something to get the state and a start link, right? And so I know that this doesn't follow all the known conventions. I cut some corners in places because I was really trying to teach concepts with the implementation of this sensor hub. Okay, so I think I've been talking long enough. Gosh, we're just within 18 minutes of finishing, but I wanted to give all of you the opportunity to ask questions. So let's open it up.
Cool. Thanks again so much, Bruce. As you mentioned, it's time for question and answer. So there is obviously the questions box in the GoToWebinar control panel that you can send your questions across. So far, the first question we had, well, at first, our friend Adolfo wanted to wish you a belated happy birthday.
Thank you, Adolfo.
And then I think facetiously asks if you ever had to try turning it off again and on again when learning this project.
Okay, so this is really cool. Adolfo is one of the brightest spots of 2020 for me. I went through some dark times that I kind of am more vocal about than I normally would be because I want programmers to take care of their health. And I was not. But Adolfo, one of our bright spots together is our involvement in this Elixir Chat mentoring group where we mentor underrepresented in Elixir. And one of the things that we do, we're always looking for metaphors. And so we believe that the official British sitcom for Erlang and for Elixir should be the IT crowd, where three customer service folks sit down in the basement and invent ways to say, did you try turning it off and on again? So thank you for that comment, Adolfo. It means a lot to me that you're
here. Next question comes from Zaki, and he asks, will the code be made available to us?
Yes, it will. So it is published on Groxio now. I have pushed the code out for the Sensor Hub already to the folks on, so that's on Groxio Learning. I will share that with Anthony. Keep in mind, when you look at the broadcaster, at the Sensor Hub, and the sensor itself, these are intended to be deployed in the Poncho project. And normally the idea of sharing a Poncho project is that you have one containing directory that holds all of the individual projects. But I wanted to be able to publish these independently because I wanted to give someone a chance to step up as a learning exercise to actually manage a sensor in the NERVS community. And this is important because very few people are doing a extraordinary amount of the work. So Zaki, thank you for your question. Yes, it'll be made available. I will give the repo links to Anthony to send out to you. And also, congratulations on your presentation to Elixir Kenya. Boy, I love that group, and you're one of my favorites too. And gosh, that was the work that you're doing for the world is just amazing. Thank you.
Cool. So at the moment, there's only one more comment from Sol, which is just thank you, Bruce. While we give people a chance to write in maybe a last minute question if they have one, I'd just like to take this opportunity again to say thank you, Bruce, for joining us. It's always a pleasure, always a really engaging and really informative webinar, and we always look forward to having you on. As you mentioned, we will, for everybody who wants to rewatch this or wants to look further into any of the things we mentioned earlier today, Groxio, the courses, this course in particular on NERVS, the repo, and the stuff we've got coming up with CodeBeam v America, we will email you all the links to that so it's all in one handy and easy to get to space. There is another we have Ilhan, just another thank you to you, Bruce, in the comments. So I think it's a great sign of a very successful webinar when 60% of the feedback is just thank you, because obviously it was comprehensive and you left no stone unturned.
Well, let me say another couple of words if to give people a chance to get some questions in. There's some interesting things going on. Thank you to Erlang Solutions for what you're doing with the CodeBeam V. It's been wonderful to kind of watch the way that you're making Zoom fatigue kind of less arduous, if you will. It's really the idea of fireside chats is a great one. I think gives us a chance to see the dynamics of conversations, which you can't get in a typical presentation. It's also kind of feeds feeds us as we're kind of going through this pandemic withdrawal. Let me point out a couple of things that are happening. So I am having a fireside chat with Sophie DiBenedetto. I think that's on the 12th, if I'm not mistaken. We're going to be talking about Phoenix Live View. And if you're interested in these CRC ideas, one of the cool things about writing and producing content is that sometimes when you come up with ideas, you get to see how other people teach these ideas and make them their own. And Sophie has definitely done that. And second, I'd like to thank Jose. Jose has, one of the important things to me is I've been wanting to get to scratch a math itch for a long time, and I've been kind of watching for the past couple of years. I've been kind of watching the math around machine learning and dabbling in Python machine learning, and so the NX announcement has just kind of knocked me out of my chair. I mean, Jose goes away and great things happen for the community. But one of the things that I've noticed is as we have talked to Elixir developers, I've noticed that well, developers in general, often the math around these concepts is pretty tough for us to break through. And so one of the things that's going to be happening on Groxio is Julia's Flux. And so I don't mean to bring this to a Beam podcast, but one of the things that it does do is gives you the opportunity to explore some of these machine learning concepts in a mathematically elegant language, where these ideas are pretty cool. But it's and then kind of bring these ideas back to the Beam, where we could actually see some see some great contributions on the great work that Jose is doing.
Yeah, that is particularly awesome. And again, I encourage people to check out all of that. We did have one more question come through just then, which was, have you considered mocking time for easier testing? I'm not sure.
Mocking time for easier testing. So in this particular API, probably the place that I would go instead is to build something like a counter function in there instead, and not use time. In the job of this broadcaster was to teach. So I wanted to show that the function that was getting called, sometimes it's confusing to people who are watching a function being shared as part of an API, what the role of that function is. Well, sometimes when you have wrapping functions like this one, the goal is to delay execution. And that's the concept that I wanted to get across, that this is in fact delaying execution, and it's only running when it's time to actually measure that sensor. So that's a great question. It's something that I would definitely do. I do that with an adapter layer. But yeah, in this particular case, it wasn't necessary.
Perfect. And that wraps up our question. Thanks again, Bruce. Thanks again, everybody, for joining us. Hope to see all of you, along with Bruce, at CodeBMV next week.
Take care, everybody.
Take care.